G'day, I'm Dr. Kev, and if I'm working on race cars, there's only one goal that you're after, and that is to win races, to be faster than other cars that are built to the same set of rules you're running to. But if you're building a sports car, it's not quite the same. A sports car doesn't get less fun just because it isn't the fastest on the road. In this video, we're going to compare race car data to road car data and look at 7 main differences that influence the design of our vehicles. Welcome to Car Design Workshop. Race cars are about relentless improvement. The example I'm going to use in this data is from 2006 when I was working professionally as a race car engineer. And this data is from a GT3 running in Sebring. We were doing around about 2 minutes and 10-second laps. Now, 20 years later, a GT3 is about 10 seconds faster. And that's faster than a GT2 from this same era. And that gets to the first point of difference between a race car and a road car, and that is speed. So there's some places in the world where you can go a lot faster than Australia, but here in my own country, the road car speed limit is 110 kilometers an hour. And of course, if you're caught in traffic, that minimum speed you could be running would be 0 kilometers an hour. Compared to this race car data from Sebring, the car has about 160 kilometer an hour average speed, and the lowest speed in a lap is going to be 74 kilometers an hour. Now we will hit 0 when we're in the pits, but that won't last very long. The top speed for the car is about 250 kilometers an hour. Now that has big implications for how we designed the vehicle. The first obvious implication is safety. The kinetic energy that needs to be absorbed in a crash is going to be a half mv squared. And so at the top speed of a race car running here at Sebring compared to the top speed you're going to hit on an Australian road, it's 516% more energy at top speed. We also know that the aerodynamic forces scale as a function of v squared. So again, the race car has about 5 times the aero loads, that means drag and downforce, that we're going to see on a road car running at 110k an hour. Even more than that, the power required to overcome drag scales as a function of VQ, which means to get any significant increase in top speed of a race car, we need a lot more power. Now, one of the big implications that we have with this, with the road car with lower speeds and often sitting at the lights at a minimum of 0 kilometers an hour, is there's going to be a lot less airflow to the radiator for a given opening and radiator size. That means a road car is going to need fans for when the car is stationary in order to keep the car cool. And because a race car is going to have a lot more airflow, you can potentially get away with a much smaller opening size. In fact, you need to tune that to ensure that you're not running too much drag in your race car. The second thing we'd want to consider is the acceleration of a car, and this is closely related to the speed. See, in a road situation, acceleration is fairly infrequent. Most of the time, you're going to be driving along freeways or long sections of straight road, which means we don't have a lot of lateral acceleration. And apart from accelerating away from the lights or braking to the lights, we don't generally have a lot of longitudinal acceleration either. Yet for a race car, the faster that we want to go in a lap, we're accelerating all the time. If you're not speeding up or slowing down or going around a corner, there's something that you've left on the table. We also notice that a race car is going to have much higher G cornering. Now this is a GT3 Porsche data, but we're still seeing cornering up past 1.5 Gs, whereas a road car, even with good tires, is only going to hit about 1 G cornering. Now this has pretty big implications. The more that you want to corner, the more lateral acceleration that you've got, the more you have to start dealing with things like, are you going to run a dry sump? Are you going to maintain oil pressure to your engine? If your engine starts to starve of oil, then it's not going to last very long. We also have suspension implications. So the more that you're cornering and accelerating, braking, the more you have to consider changes to camber and to ride height. It's one of the reasons a race car is often a lot stiffer than a road car. And the third thing I want to consider is the throttle usage. On a road car, there's a lot of low usage of throttle. The example we have here from the road car, even though it was a fairly lively drive in a Caterham, we still only hit about 8% average throttle. And that's because there's a lot of time spent either cruising at a constant speed or stopped at a set of lights. Whereas we see on a race car, the throttle is very on or off. It's almost digital. and the average throttle usage for a lap around Sebring was 66%. Now that means that there's a lot more of the power of the engine being used, which has a big implication on our cooling system. It means a lot more heat is coming out of the engine that we're going to have to deal with, which leads to our fourth point. The engine speed we're going to see is also a lot higher for a race car than a road car. In a road car, it's very low. For the short run that we have here, we only had an average of about 1700 RPM. Now you will see in a spirited drive your RPM being a lot higher when you're taking off from the lights, and you might feel like you're revving it quite a lot, but because you just can't keep going faster and faster on the road, at some point you need to cruise, and you've got to put that into a higher gear. Whereas on the race car, we have an average RPM that's very high, of about 6,900 in this situation. That's higher than the red line on a lot of road cars. Now this has a massive impact on the amount of heat that is being generated. In a road car, over an average period of time, you've got a lot less heat. And heat transfer is time-based, so we can have a cooling system that is designed for quick acceleration off the line that might not be able to handle that non-stop. There's a capacitor-style effect of water. We don't need to size the cooling system of a road car for maximum power output or maximum RPM output. And one of the common issues that we have if we take a road car that's designed for the road and put it on a racetrack is it'll often overheat. Because in a race car situation, you're going to be using much more of that power more of the time. Now, it also has some pretty big implications on the engine life. In a road car, you want your engine to last a long time. So we want to keep the revs pretty low. In the race car, running at these higher RPMs have pretty big implications. It means we're going to need stronger materials. We need a better balanced engine. We've got to think about the kinetic energy of components. Friction and the oil leads to RPM dependent friction. And if we're doing long distance racing, the best sort of racing, you could have 6 or 12 or even 24 hours of hard load. Now in a 24-hour race, you could be doing 4,000 kilometers of high load in a GT3 car. Now there are some other implications around tuning. So if you are going to be running at a higher RPM, like a race car, you're generally going to want things like shorter runners to tune your peak torque at a much higher RPM than you would have on a road car. Now, if we're going faster and we're still hitting corners, that means our brakes are used in a very, very different way on a race car than they are on a road car. On a road car, we're generally applying our brakes very smooth and building up some pressure, not just slamming them on and using the maximum amount of braking. Now, also, we're generally operating them infrequently. So that means our brake system is usually cold when we're applying the brakes. In a race car, the brake application is very aggressive at the start, almost maximum braking near the start of that braking zone, and then tapering that off as you're trail braking into the corner, ensuring that the front is not locking up. And a driver, in order to be this aggressive on the brakes, needs to rely on set braking points around the track. And these aggressive braking maneuvers, they're happening over and over again in a lap. It's repeated high braking. It means the temperature of the braking system is going to be quite high. It means the brake pads that you're going to use are going to have to be designed to give good friction at high temperatures, rather than on the roads where we might want brake pads that give you good friction from a low temperature. It also means that our fluid needs to withstand much higher temperatures before boiling, and we need to think about the amount of material and size of our brake discs to ensure they have decent thermal capacity. We also need to think about cooling for our braking system. And just like we would have with the engine cooling, brake temperature and overheating of the brakes is a regular failure point for road cars going on track. Sometimes you can take some very fast road cars, put them on a decent track, and they'll only get a few laps out before their brakes are overheated. And that brings us to our sixth point, which is the track. If we're dealing with a road car, we could be dealing with any surface. It could be a bumpy road, it could be potholes, it could be speed bumps, dirt. Whereas on a race car, even the bumpy tracks, if we're talking circuits, are generally pretty smooth. We saw this year that they actually stopped the Monaco F1 race because of a hole in the track. Yet around the corner from my place, they haven't stopped traffic because of a whopping great big pothole there. That means for a race car, we've got a different approach to our suspensions. We're going to be dealing with generally lower damper speeds. It means we can run the car a lot stiffer. For a road car, the stiffer we make it, the less capable it's going to be as the roads get rougher. Now, we also noticed that there's safety implications. Roads are shared with all sorts of people. There's trucks, there's cyclists, there's pedestrians, there's cars going all sorts of directions. There's a lot less predictability than there is on a racetrack. On a racetrack, the same thing tends to happen lap after lap. All the cars are heading in the same direction, they're traveling similar speeds, and while exciting things might happen every so often, it's far less possibility than what you might have on a shared road. That means a road car needs to be further away from the limit and build in some more capability to deal with any odd situations. So much of what is done around racetracks is to improve the safety of these higher speed vehicles. You've got runoff areas that are much better for safety, able to slow the cars down before a collision. You have tyre barriers to absorb energy. So that means that you can drive to the limit much more safely. So there is an assumption in racing that there are going to be accidents, and the track design accounts for that. Also on a racetrack, a lot of effort is made to separate people from the cars. There's barriers between the racetrack and spectators. If you were to drive on the road like you drive on a racetrack, there's far more chances for something seriously bad to happen. And the seventh point that I wanted to bring up is just the difference in the driver. In a race car, you're generally dealing with somebody that's a little bit more skilled and experienced. A good race driver is very repeatable. Lap after lap, we're going to see the same sorts of inputs at the same sorts of time. If you overlaid many laps, often you see very little differences from one lap to the next. A good driver is fit and strong and has endurance, and they can handle higher inputs. They're generally more accurate with their input, and there is a much smaller margin for error. Whereas the driver of a road car could be anybody. So the car just needs to be a little bit more forgiving. There's a different trade-off we make for comfort versus performance. Now, we don't want to make a race car completely uncomfortable because that means it's going to be too hard to drive at the limit. But that trade-off is at a different point. So we would accept a much higher level of vibration and heat and loads on the driver in a race car than we would in a road car. Now, you could potentially spend a lot more time in your road car than you ever would in a race car. So things like noise become pretty important. I would generally drive around 10 hours per week in a normal week, which is about 500 hours per year sitting in a car. And if I want to take a sports car on a long trip down south in Western Australia, I'm going to want to make sure that's a little bit more comfortable than my race car might be. Now, we get a fair few questions on this channel about why we don't just build Project 171 as fast as we possibly can. We get asked, why would we want to compromise performance when we can just make it a little bit better? But I think once you see the differences of a race car compared to a road car, you probably realize that you don't actually want a race car on the road. You just want something that gives you the feeling of being in a race car. So I'm pretty keen to hear your thoughts about the differences between road cars and race cars. So feel free to leave a comment on this video on your way to liking it. And if you want to continue seeing how we're working on this sports car, please subscribe to the channel. Thanks for your time.